postdoctoral fellow in geophysics, and as I found out a few weeks ago, also my neighbor. You're a historian.
So Eric asked me to give a talk about climate, and I do work on serious future climate stuff, but I thought it would be fun to talk about weird, wacky climates that people might not have heard about before. So Earth's climate has done a lot of very strange, weird stuff over the past 4.5 billion years, including more recently in North America, we had beasts like that and that about 15,000 years ago. So this is an elk, and this is a giant sloth, just for scale. And this is a woolly mammoth. So if you want to go on safari in Africa, you would have had a vastly better safari in North America 15,000 years ago. And all of a sudden, these guys just went extinct. So I'll talk a bit about why that might have happened. And if you go, so these were sort of the cold glacial climates that prevailed over the past couple million years. If you go further back in time, you get into these very warm climates where mammals evolved. And this is an example of that. So there were climates much, much warmer than today, tens of millions of years ago. And before that, you go into the dinosaur period. And way, way long before that, 600 million years ago, you get into these potential snowball episodes. And those are probably the weirdest and wackiest climates that Earth has ever experienced. And so you have all these extremely different, wild, crazy climates that have happened. And sometimes you have switches between them that happen very rapidly. So that's what I'm going to talk about. But first, there's been this Climategate scandal, so I thought I should address that briefly. And it looks, some of these emails look pretty bad. So these are stolen emails from these researchers in England. So this is, a climate guy, and he says he just completed Michael Mann's nature trick to hide the decline in temperatures. So it looks like some sort of great conspiracy of climate scientists. And here's Caesar, the public, lying mortally wounded. And the climate scientists are celebrating here. And it turns out that we tend to look more like German barbarians than Roman senators. But anyway, so there's the question of what are they talking about here? And is there some conspiracy that we're hiding things from the public? Like what's important is, one thing that's important is that date, 99. So what they're talking about is tree ring reconstructions of recent climate history. So before I go too far, I just want to say all the time scales on plots I'm going to show, sometimes they're going to be in hundreds of years, sometimes they're going to be thousands, and sometimes millions. So you have to pay attention to what it is. But here, this is just years AD. And so it's the past couple of thousand years. And they try to figure out sort of what the North American climate was, Northern Hemisphere climate was, Northern Hemisphere mean temperature, based on looking at things about tree rings. And this plot's from 2009. And what we show over here is the instrumental record, what people have measured, mostly British, going around in their empire. And this is the climate reconstruction based on tree rings. Things like how dense the rings are, how wide they are. It's supposed to tell you something about growing season temperature. And the issue is here. This is their tree ring data from 1880 to 2000. That's these wiggly lines. Well, it's hard to sort them out here, but these wiggly lines here going back. And this is the temperature in the growing season that they're supposed to correlate with. And so the idea is that the temperature looks pretty close to the tree ring data until 1960, and then it deviates. And so that's the fix that they're talking about. So basically, what it means is that we're not sure, there's some deviation between tree rings and the temperature they're supposed to represent over the past 50 years. And we don't actually know why that is. But they use this correlation to reconstruct the past climate. But the point is that, so you can debate whether tree rings are a useful measure of past climate. That's fine if you want to debate that. But this is published in '98, and it's well known in the literature that there was this issue. And it's not like climate scientists are hiding anything. So, I mean, there's some other issues with these emails, but if anyone wants to talk about this more later, we can. I thought I'd just mention that before we get started. But anyways, now back to the real wacky climates. So why do we study these? What's the point of studying weird climates in the past? Why is it a useful enterprise? Probably the best reason is because we want to improve these climate models that we use to forecast future climate. So what is a climate model? This is a little diagram of one. We know the equations of fluid flow, the Navier-Stokes equations, partial differential equations on a rapidly rotating sphere, which is the Earth. And these describe how the atmospheres and oceans move around on Earth. We also know the equations of radiative transfer. And we discretize these like this and solve it on a supercomputer to see what the climate will do if we do things like increase the CO2. So that's what a climate model is. The problem is that these boxes here are, in the best models, about 100 kilometers by 100 kilometers. And there are a lot of important processes that are smaller than that. So clouds happen on very small scales, hundreds of meters. And they even have microphysics on, a micrometer sort of scale. And so to figure out what the clouds are going to do, you have to take some variable on the grid scale and make some parameterization to figure out what the clouds will do. So we'll say a grid box has a temperature of such and such and a relative humidity of such and such. Therefore, we'll have 50% cloud cover. And those are empirically based parameterizations. So essentially, the climate model is a machine that, in some sense, it's an interpolation device based on the modern climate. And we're trying to extrapolate to different climates with it. And that's where climate uncertainty comes in. So if we look at the severity of future climate change, there's some uncertainty in how severe it would be. And this is the basic process that's driving that uncertainty. So wacky climates are something that's very different from modern. So if we put the, we collect some data to figure out what was happening in the wacky climate, then we try to make the climate model simulate it, and we can try to figure out what's wrong with the climate model when we extrapolate. And hopefully, by doing this, we can improve the climate model and decrease this uncertainty. So that's sort of the first reason we would do this. The second reason is there's an interface with biology, because a lot of these branches in the tree of life happen during weird, strange climates. So strange climates force evolution of life. Some of these climates are so weird, like the snowball, that it's almost like it's a different planet we're talking about. So studying them may tell us something important for the astrophysics community that's discovering these exoplanets. It may tell us what we can look for and still think that possibly life could survive, because we know we've had really weird climates here, and complex life did evolve. And finally, it's fun. So just to orient you on the timescales here, this is a geological chart of Earth's history, and time goes here. And we're going back, and these are millions of years. That's important, millions of years. And we're going back to 3.8 billion years. And the solar system is about 4.5 billion. So we're really going back a significant fraction of that time period. And I'm going to talk about sort of three periods. The first is the glacial cycles, then what we call equable climates, and snowball Earth. So we live up here in the Holocene, the past 10,000 years, of a very, very, very stable climate. But before that, there were these wild glacial cycles, where every 100,000 years we would have extremely cold conditions, then extremely warm conditions. And within that, imposed on that, were very fast variations in climate. So I'll talk about that first. Then, basically, as you go back before about 35 million years ago, there's this long, broad period of very warm climate. And there's no ice, really, no significant amount of ice anywhere on the planet. So we have a very warm climate, much, much warmer than today, in this long, broad, equable climate period. And this is an important period because this is sort of the dinosaur period, the early mammal period. So it's a very important period for life on the planet. And then way, way back, long ago, there are these potential snowball Earth episodes. There's a good case for one 635 million years ago, and somewhat weaker cases for them 710 and 2.2 billion years ago. 710 million, 2.2 billion. And so that'll be the last thing I talk about, hopefully, if there's time. But this is really the wackiest of all the wacky climates. So I'm hoping we'll get to that. So first, the ice ages. And this is a diagram of where there was large ice sheet cover at the last glacial maximum. And as you can can see, where we are today, there was an ice sheet. And these were very thick ice sheets, kilometers thick. And now it's retreated all the way back and only covers Greenland. But the last glacial maximum, a large part of northern North America was covered in ice. The other important point is that because of all this ice, the sea level was fairly lower. So you could actually walk across. It's called Beringia, this land bridge between Asia and North America. So how do we know? How do we know about this type of thing? So one popular way to figure out what was happening in Asian climates is to look at these foraminifera. These are tiny protists that are planktons that live in the ocean. And they either live at the bottom or at the top, different types. And long ago they lived, and they have a shell of calcium carbonate that grows. And then they die, and they fall into the mud. And then we come along, and we dig into the mud. And the further down you dig, the further back you go in time. And then you measure the oxygen isotopic ratio in the shells, and you try to reconstruct climate from that. Now, the oxygen isotopic ratio in the water increases if there's a lot of ice on land. And the reason is that light isotopes preferentially evaporate. So what's left in the water, so you evaporate lighter isotopes preferentially, and then you snow them out and make glaciers. And so the glaciers are very light in oxygen, and the water that's left behind is heavy, and we can detect this. It also turns out that in the process of making the shell, so this is a diagram from growing these shells in a laboratory, there's a temperature fractionation. And when it's colder, you tend to get the shells heavier in oxygen 18 as compared to seawater. And when it's warmer, you tend to get them lighter. So if you measure the oxygen 18 isotope ratio of these shells, when the ratio is higher, that means there's more ice and it's colder. And when it's lower, that means there's less ice and it's warmer. So here's what happens when you do this. For the past couple million years. And what this shows is, so this is time going the backwards way. A lot of these diagrams make time goes this way. So these are years before present, thousands of years before present. And when this number goes down, the delta 18, this is a reversed axis, that means that things are warmer and there's less ice on the planet. And when this number goes up, or down on the plot, that means it's colder and there's more ice. And this is a large ensemble of these different mud cores from around the planet. That's what's being plotted here. And the delta 18 of these blankets. So what you can see is that for about 800,000 years, we've had one of these cycles, and these are ice age cycles, about every 100,000 years. And they have a very sawtooth structure. So if you follow here, this means this is an interglacial period, this is the Eemian, and slowly you build up big ice sheets and it gets colder and colder. And then all of a sudden, this is the last glacial maximum, and then you shoot up into an interglacial period that we're in now, the Holocene. So you have these sawtooth structures with about 100,000 year time scale, and then for some reason before 800,000 years, you have more like smaller cycles that have a time scale of more like 40,000 years, and that are much more symmetric. And we know that what's causing this has to do basically with the changes in the orbital configuration of Earth, slowly wobbling as it's going around the sun over tens of thousands of years time scale. But the problem is that we can't exactly explain why that's causing these. So it's still a mystery. And we also can't explain why there's this switch. So there's still mysterious things about the ice ages. Okay, so this is the mud. These are the foraminifera in the mud. But it turns out we can also go dig into ice on Greenland and Antarctica and try to figure out what the climate was like based on that. So you dig a big ice core, and this is one of these ice cores, and the guy's over there in some sort of refrigerator. Possibly they're still in Antarctica. And then as you go further down in the ice, you go further back in time. And when you do this, you can measure a different isotope. It turns out deuterium is more important for Antarctica. That correlates with temperature. And you can also measure the air bubbles in the ice to figure out atmospheric composition, things like CO2. And if you go back over the last 400,000 years here, so this is years before present, back to over see that temperature and CO2 are highly correlated. So Al Gore made a big deal out of this in his movie. We don't know what's causing what exactly. So they're definitely related. What's probably going on is that CO2 is a positive feedback. So something else is causing the temperature of the ice to change. And then that's causing the ocean to somehow adjust to change the CO2, which causes further cooling or further warming. But we don't know exactly why the ocean adjusts to make such big swings in CO2. So this is also still a mystery. A very interesting thing people are studying. Okay, but the point is that this is an entirely independent source of data, and we get the exact same result. We can only go, the ice sheets in Antarctica only go back 800,000 years, but it's amazing that if you look at the foraminifera and the mud, or if you look at the ice sheets, you see exactly the same thing going on. So we're very confident that these ice ages were happening at the time scale.
Do the peaks correspond in the foraminifera and the ice sheets?
Well, yeah, so, yeah, the problem is dating these things is sometimes difficult. Getting the time scale, so going from the depth you dig to the time it happened is difficult. But as well as we can tell, they do. And it would be really weird if they didn't. But yeah, that's an issue. Okay, but it's not just these slow 100,000-year cycles that are happening in the glacial period. It turns out there's really, really fast stuff happening. So there are entire reorganizations in the global climate, in the temperature, in the precipitation, in dust and methane, which is controlled by basically tropical precipitation. All of these things change on decadal timescales all over the globe. And this is an example of that. So this is an ice sheet from Greenland, and it's an isotopic measurement that indicates temperature. And here we're talking about years before present, and that's 10,000, and that's 20,000. So we're in the middle of the hard glacial maximum back here. And all of a sudden, within, basically decades at the most, we jump, the temperature jumps up, and it gets as warm here as it is at present. All of a sudden, decades. And then for 1,500 years, we have a warm climate, kind of like we have now. And then all of a sudden, it jumps back into this very cold climate. And then it jumps again here, also in decades. And then we just continue on in the Holocene for the next 10,000 years in a warm climate. So there's some very weird, jumpy things happening that indicate strong nonlinearities in the climate system. Let's see. Right. This warm period is called the Bowling Alrod, and this young period, this is called the Younger Dryas, this cold period. But the important point is this other isotopic ratio is measured from the calcium carbonate in stalactites and stalagmites in Chinese caves. And these caves exist in a position where sometimes if there's a strong monsoon, they get rain from the Indian Ocean. And if there's a weak monsoon, most of their rain comes from the Pacific Ocean. And the delta 18 of these two source regions is vastly different. So when these wiggle up and down, it means there's a change in the source region. And you can see that there's a change at exactly the same times. And the dating is better on this time scale because they can use carbon dating. At exactly the same times as you see these temperature changes in Greenland, you see huge shifts in the precipitation in China. So there's really a global phenomenon and a reorganization on very quick timescales. The important thing is that we can't simulate these in climate models. So there's the potential that we could get something like this in the future. Yeah?
How do you tell what the temperature is 100,000 years ago?
Well, there are various methods, but that's...
Sorry, just from the oxygen it tells you?
Yeah, this is one of the... Usually you do it with things like isotopes. There are various methods, but...
I'm sorry, I should have paid attention.
This is... this temperature fractionation tells you something about temperature.
Okay.
The problem is with oxygen isotope, it's tied up with how much ice there is. So it's hard to deconvolve those. But they also use other isotopes like deuterium in other places. But the most common methods have to do with isotopes of stable isotope stuff. But also these tree ring guys try to do it with tree rings. There are various methods. Okay, right. So what does this have to do with human type things? Well, back to the megafauna. It turns out that all of these megafauna, the last bones that we find are between about 11,000 and 13,000 years ago. So it's right in this period when there's a lot of weird stuff happening. And there's been a long debate about what caused the megafauna to go extinct in North America. One idea is that it's these wild changes in climate that did it. It also turns out that at roughly the same time scale, the first technologically advanced people showed up in North America, the Clovis people. They had very sophisticated tips for their spears, and that's what we find and how we identify these people. But they also had these special slinging devices to accelerate their spears. So they could, a number of them could drive these spears at high velocities into these animals. And we know that where we find these Clovis tips, we also find the butchered bones of megafauna. So there's no question that they were eating the megafauna. But we don't know for sure that they caused the extinction. And sort of the hard Clovis hypothesis is that the megafauna were going along just fine and happy, and the Clovis showed up and hunted them all to extinction. There's also this asteroid idea. Now, you may have heard of the asteroid that killed the dinosaurs 65 million years ago. That one is much better supported by data. But there's also the idea that there was some asteroid that destroyed the megafauna, 11,000 or 13,000 years ago. And I think this one is a little fanciful. So I think it's really the contenders are the Clovis people and climate change. And so there was a very interesting new dung proxy that was published a couple months ago that has helped to resolve this issue. So there's a number of plots here, and really the only one that's really important for this point is this one. This, basically, that's dung fungus spores. So they go in lakes around North America. This lake is in Indiana, and they repeated this process in a few different lakes. And basically, when you have these megafauna, when you have a large herbivore grazers, they produce these large dung piles, and fungus grow on them. And their life cycle is they live on a big pile of poo, and then they fling out their spores. And the idea is to try to fling them far enough that some will land on a different pile, and then start the life cycle again and repeat. So they dig down in the lake, and they just count the number of spores they find. And the idea is that this should be somehow correlated with the size of the herd near the lake. And what you can see is at 14.7 thousand years ago, really a sharp decline starts in this proxy. And by about 13.7, it's basically zero. There's some noisiness here, but it's under 2% of what it was over here by 13.7. And so now we can compare that to the dating of the other ideas, and that's what I've done over here. So the decline starts at 14.7, which is within the dating error, exactly correlated with the rapid switch to that warm climate. So the megafauna existed in a cold glacial climate, and there's a rapid switch to a warm climate like we have today that's much moister, and that correlates exactly with the decline in the fecal spores of the megafauna. It pretty much ends at 13.7, so there may be a few survivors around, but the herds are already decimated by 13.7 kiloyears. And we don't start to find the evidence of Clovis people for another 700 years. The potential asteroid impact that may have happened is almost the same time as the Clovis people. And this other climate change, where you go back to the cold condition, happens at 12.8 kiloyears. So this to me is fairly strong evidence that climate was really the dominant driver in driving down the herd populations. It's still possible that the Clovis people finished them off. This doesn't rule that out. But it means that the hard Clovis hypothesis, that the animals were happy and the people came into North America and finished them off, is pretty much dead now. However, the commentary on this article in Science was written by an archaeologist who's really stuck in the people mode. And he said, this is strong evidence that there must have been some other people before Clovis people who came and killed them. And I think that's pretty unlikely. This tells us that it was probably climate change that drove them down. Okay, so that's the end of the story about cold glacial climates. And now I'm going to talk about something on a different time scale. So instead of the last 2 billion years, now we're talking about a very broad, warm climate, equable climates that existed for tens of millions of years, roughly 50 million years ago. So, and these are just artist pictures of the sorts of things that happened. And basically, the entire planet was a tropical paradise. So in Alaska, there were palm trees, there were crocodiles in the Arctic Ocean. Things were totally different. And before I get into that, you probably are familiar with this, but the continents can move around. And so over tens of millions of years, things didn't necessarily look exactly like they do now. And this is a reconstruction of what the planet looked like during the middle of this warm period, 50 million years ago. So the broad outline is similar, but the Atlantic Ocean is smaller, the Pacific is bigger, India is a little further south, Australia is closer to Antarctica, and the sea level is higher. So you have the Mediterranean becomes this large Tethys seaway that connects the Indian Ocean and the North Atlantic. And there are large interior seaways inside the continents. And why do the continents move? Just briefly, the rock in the mantle of the Earth actually convects. So you have convecting rock, and the convection drags along the continents on the surface, and the continents are also more dense, so when they enter the mantle, they pull. And some combination of these convective cells and the pull of the slabs causes things to move around. And how do we know where things used to be, where the continents used to be? Well, it turns out that there are certain rocks that preserve the magnetic field that they felt when they formed. And you go find those particular types of rocks, and you look at the orientation of the magnetic field. And we know that the magnetic field of Earth can switch between poles, but it doesn't spend much time switching. It's generally either oriented this way or oriented in the reverse way. So it just switches back and forth. It doesn't stay near the equator. So you interpret the magnetic field as a sign of the latitude. And if the lines are relatively vertical, you know you found the rock near the pole. And if they're relatively horizontal, you found the rock near the equator. And then you sort of do a jigsaw puzzle to try to get back to what the climates look like in longitude. So it's similar to old-fashioned navigation. You can figure out the latitude well, but you have to do a sort of a dead reckoning to try to figure out where the things were in longitude. And how do we know about the climate back then? Well, there's a few different ways to try to reconstruct the climate. The easiest way, and the one that's been noticed for a couple hundred years, is to just look at the nearest living relative. So, for example, there are certain types of species that are very strongly controlled, their survival, by the climate. One example is a palm tree. There are 1,000 species of palm trees in the modern climate, and none of them survive extended frost. If you put them in a frost for a few days, they die. There's a physiological reason why that is, related to the water flow in the flesh of the tree. And the fossils that we find, they show the signs that they had that same issue. So if you find a palm tree fossil, it's very strong evidence that there were no extended freezes where you found the fossil in the time when the fossil grew. And just an example, we find these in Wyoming, where now you can have a few days of minus 40 at night. So it couldn't have dropped below freezing in the middle of North America, in the middle of winter. We find recently there was a lot of effort to get the first ocean mud core at the North Pole. And they actually found the pollen of palm trees 50 million years ago in this core. So it's very strong evidence that it didn't drop below freezing in the Arctic Ocean during polar night. And similarly, cold-blooded animals like crocodiles aren't happy if it's snowing and below freezing. And if you find these in islands at 80 degrees north of the Arctic Ocean. So this is not a quantitative way to reconstruct climate, but it's fairly foolproof. It's not like looking at oxygen isotopes, where you can debate what exactly the signals mean. When you find these guys, we know something was up. And going to sort of semi-quantitative methods, it turns out that if you look at a forest, and maybe there's 100 species of tree in the forest, and you count up the fraction of the tree species that have smooth leaves and wiggly leaves, it turns out that that fraction is correlated with the temperature, the mean temperature of the forest. So if you go from north to south on the Americas, and you do sort of a transect, measuring a bunch of different species, measuring a bunch of different forests, measuring all the species, you can develop sort of a correlation. And then you go back, and we actually find whole fossil forests. You can find fossil forests with 60 species from the exact same time period. And you count the wiggly fraction and the smooth fraction, and you're trying to get the mean annual temperature. So the error bars are high on this method, but it is a way to start to get a quantitative estimate of what the temperatures were, a number.
Wiggly likes the warm temperature?
Wiggly likes cold. And the physiological reasons for this are not completely understood, but it seems to have to do with something. So a large leaf, wiggliness is like sort of a perturbation. But a very small leaf, a growing leaf bud, the wiggliness is really a first order effect. And it seems to have to do with, in cold temperatures, the fluid flow in the leaf, it works better if it's wiggly.
Is there a correlation between bark, rough bark, and smooth bark?
I'm not aware of one, but yeah, I don't know if there is. And also these foraminifera, they were nice for the glacial cycles, but they also go back close to 100 million years, so we can use these guys as well. And this is a curve using these foraminifera. So this is a very famous paleoclimate plot, and it's showing us in the age and millions of years before present what the delta 18 up here of the foraminifera in the deep ocean were. So it's sort of a zero-dimensional picture of what the climate of Earth was. Something about how much ice and how cold it was, sort of averaged over the whole planet. And the first thing you notice when you look at this plot is basically since about 50 million years ago, delta 18 has been increasing in the deep ocean. And what that tells us is that it's been getting colder and there's been getting more ice. And we can actually see where there's ice on this plot. You can immediately see that back here, things are relatively, the dots are relatively calm, and here they're crazy. And that's a sign of ice, because it's easy for ice to change the delta 18 a lot just by growing and shrinking these ice sheets. And here you can see the glacial cycles where you really get wiggliness. And we have North American glaciation back for this period. And as you go back in time, eventually, this corresponds to the growth of the Antarctic ice sheet, but eventually you have basically no ice on the planet. Now, once there's no ice, delta 18 is just a measurement of temperature. It's not a measurement of ice anymore, because there's none of it. And when that happens, this temperature scale down here, it corresponds to what you can back out from the delta 18 measurement in terms of deep ocean temperature. And at the optimum, I should say, frequently these delta 18 guys refer to this as the climatic optimum and the degradation of climate over this time period. So they sort of infuse the discussion with normative terms. But basically what they mean is that it cools. At the warmest temperatures in the past 70 million years, the deep ocean was 12 degrees Celsius, whereas now it's more like -1. So the entire ocean wasn't just surface effects. The whole ocean was much, much warmer. And the only other thing I want to point out is this spike right here. It's labeled Late Paleocene Thermal Maximum. Now, when this paper was published, they considered that spike as happening in the end of this period. Now we say this spike separates this period from that period and call it the Paleocene Eocene Thermal Maximum. But the point is that basically as fast as this record can resolve, about 10,000 years, the global mean temperature went up by 4 or 5 degrees Celsius. This is oxygen isotopic ratios. We also have carbon isotopic ratios. And they show that the CO2 got extremely high during that period. So it looks like this is some sort of an analog for the modern experiment that we're conducting.
Where did these foraminifers come from?
Yeah, so this is a collection of a bunch of different ones from different ocean cores around the planet.
Okay, so they're mixed bunch, mixed.
Yes,
bunch.
exactly. But the idea is that the delta 18 value of the deep ocean should be relatively constant. On the surface ocean, it changes a lot. But yeah, they're assuming, there are a few things they're assuming. One is that it's relatively constant around the planet. The other is that so some species come into existence and go extinct over this time period. They're assuming that the interspecies effect effects are not too strong.
What's the cutoff in depth?
So thanks.
What do you call deep?
Yeah, I mean, I think they're basically talking about more than a kilometer.
Really?
Yeah.
Where are we now?
Yeah. You can't see where we are. So this is millions of years. So what, if we call us maybe like since the Roman period.
But where is on the horizontal scale?
Oh, right. Yeah, that's easier to see. Yeah. That's easier to see in this one. This is the same plot, but only for the past 2 million years. We're right up here at about 3. Yeah. So we're here right now. We're at an interglacial in the glacial cycle period.
You mentioned CO2 levels rose during that
Yeah.
time. From what source?
From what to what?
From where the extra CO2 come?
Yeah, well, there's some debate about actually whether it was CO2 or methane that did it. But some greenhouse gas, I sort of glossed that over. We know some greenhouse gas rose, and the answer is nobody really knows. My personal opinion is that the strongest possibility is there was a lot of carbon in the biosphere. Things warmed up so much that it killed the biosphere, and all of that stuff burned and put it into the atmosphere. Something along those lines, but we don't know.
Would just the decay put the carbon in the atmosphere?
It does, yeah,
rather than
but
burning?
it could, yeah. If it died and decayed, that would also do it. Yeah. Right. So what about the surface temperatures? What about trying to get more than a zero-G picture of what the climate was like then? So that's what these guys have tried to do. This is from Wyland in 95. And what they're looking at is the mean annual temperature as a function of the latitude and the cold month mean temperature. So this would be the temperature in June in the northern hemisphere, or July in the southern hemisphere. And what you have here in the dotted line is the current mean annual temperature as a function of latitude, and the gray is sort of the range as you go around the planet. And all these dots are various types of paleo data. And same thing for cold month, paleo data that give you cold month. And what you can see from this plot is during this period, so this is sort of the middle of this warm equable climates, the temperature that these data indicate at the equator is about the same as what it is today. But at the poles, it's extremely much warmer. So it's not just that everything was warmer. It's that there was sort of a leveraging. It was much, much warmer at the poles. This is why we call these equable climates. So we say the poles were more equal to the equator, and the winter temperatures were more equal to the summer temperatures. So we call them equable climates. But this has been very difficult to understand. So one thing people have thought about doing is that, well, maybe the CO2 was just much higher then. And unfortunately, we only know the CO2 back 800,000 years. And before that, the ice sheets don't preserve any air bubbles. And so we don't know what the CO2 was. People try to make various types of proxies based usually on the ocean pH, to try to figure out what the CO2 was during these periods. But the answer they get is that it was somewhere between 500 and 5,000. And on this scale, we're at 400 now. So basically, there seems to be evidence that it was higher, but we don't really know what it was. So people think, well, we'll just take a climate model, and maybe if we move the continents around and increase the CO2 a little, then we'll be able to simulate these equable climates. And that approach was tried. In this case, the best model that was available in 2001 was used. And this is the sea surface temperature as a function of latitude, South Pole, equator, North Pole. The dotted line is what the model does in our climate. The red line is what it did in the Eocene climate, where they increased the CO2 by 560 parts per million. And the blue line is what the data they were trying to match indicate. And so this is the problem. This is the problem with trying to simulate equable climates. If the tropical temperature temperatures have to be roughly what they are today. As you increase CO2, it gets too hot in the tropics before it gets hot enough at the high latitudes. And so this is why people have studied this issue, because it might indicate that there's something wrong with the models, potentially, that we want to try to understand better. So that's why, yep.
As I understand now, the poles are getting warmer, not colder, like you described. You just said that the poles were not as warm as the tropics. They didn't change as fast, but today we see.
Yes. Well, the idea is that we might be going into a climate like this. Is the idea, or you're talking about there's a stronger warming is occurring at high latitudes than at that is correct. And the idea is that potentially we could be going into something with a flatter temperature gradient, and so that's why we want to try to understand this process. Right. So I said clouds are a thing really difficult to simulate in these models, and this is something I worked on, trying to understand whether there could be some missing cloud effect or in the models that could explain this discrepancy. And it turns out that clouds have a lot of different effects in the atmosphere. So the insulation that's coming at the top of the atmosphere is 344 watts per meter squared, globally averaged, annually averaged. Clouds reflect 100 of that away, and they have a warming effect, absorbing infrared radiation from the planet of 80. So they have a minus 100 and a plus 80. So they're really huge terms in terms of global energy balance. If you got rid of the warming effect of clouds, we would be Mars. And if you got rid of the cooling effect of clouds, we'd be Venus. So they're really huge. And the low clouds, they radiate at nearly the surface temperature. So they can have very little reduction in the outgoing long-range radiation. So they can warm things only a little bit. However, they can be very optically thick and visible, so they can reflect a lot of sunlight and have a big cooling effect. High clouds, things like these thin cirrus clouds, they can let a lot of light through, like a cirrus would. However, they radiate at such a low temperature that they can have a very strong warming effect. So how do we get these clouds? There's various different ways, and one of them is atmospheric convection. So the basic idea is you can have an air column that's stable to small perturbations in the atmosphere. If you perturb an air parcel upwards a little bit, it comes back down to where you stuck it. But slightly larger perturbations, it becomes unstable. And that's what causes atmospheric convection. And the basic idea is you would take an air parcel from down here, and you bring it up to this layer. This is a very important layer here, where the water vapor in it starts to condense. And if you perturb up that high, as the thing expands and cools, and you start to condense water vapor, it releases heat. The heat released warms the parcel further, and then you have this huge instability causing these plumes going upwards, and a very buoyant air. And as this happens, whatever, you keep repeating this, rising more, condensing more water vapor, releasing more heat, rising more. The water vapor you leave behind, it either falls out as rain or it stays behind as a cloud. And that's what interacts with the radiation. Now, these clouds, they can also have plumes coming out like this and generate lots of high clouds that can have a strong warming effect. So sort of that's what we were thinking about. And the feedback that we proposed was that you warm the surface, then this destabilizes the air column at high latitude. So currently you have a stable air column and lots of low reflecting clouds. It causes deep convection, high clouds, strong greenhouse effect, and a warmer surface, and you get this feedback like that. So that was what we proposed, that there could be something like this. And basically, our idea was not that it was missing from climate models, but that you had to increase the CO2 enough that it would actually turn on. And that once you hit a critical threshold, there would be sort of a nonlinear behavior, and all of a sudden this would turn on. And it turns out that this seems to work in climate models. And there has actually been newer tropical data. So this is millions of years before present and tropical sea surface temperatures. And these are newer data since '95, so 13 years later. And these data temperature may have been 3 to 5 degrees warmer than it is at present. And there are even some data that indicate it could have been much warmer than that, but we don't believe those because if the sea was that warm in the tropics, all of the plants in the tropical region would suffer heat stress and die, and we have no evidence of that. But if you're allowed to make the tropics even a little bit warmer, you can start to simulate adaptable climates in a global climate model. And so this is the results of such a simulation, and these are the continents moved around like I showed before for the Eocene. And here, instead of turning the CO2 up to 560 parts per million, he's turned it up to 2240 parts per million. So 8 times pre-industrial value instead of just doubling it. And the contours are his annual mean temperature. And these stars are what he considers the best data for the time period he's simulated. And they're also colored with the same colors as the contours. And you can see they basically line up fairly well. And in this model, this feedback actually turns on if you get the CO2 high enough. And that's part of what helps it explain the ethical climates.
How high is it?
8 times pre-industrial.
Which it will be?
2,000 parts per million.
So we are far from that.
We're far from that. But there is an issue here that all of the climate that, this is the US national climate model. The German one from the Max Planck Institute does this at only 560 parts per million. However, they have to get rid of the ice sheets and they have to move the continents around to get it to do that. So it doesn't mean that in our current experiment we'll reproduce an Eocene yet. But if we get it high enough that we can melt all the ice sheets, we could potentially reproduce this type of behavior. So, yeah.
When you describe the position of the continents,
Yeah.
The currents that they could bring and change the temperature
Yeah.
were totally different than today.
Exactly, yeah. Well, it turns out that there are some important aspects of that. So, if you mean ocean currents, it's true that the ocean, this model solves for ocean and atmospheric currents. And it's true that there is some effect. And it turns out that that's a really, there's a paper that came out this year showing how important that is for the Arctic Ocean. So whether the Arctic Ocean was sealed off or there was even a tiny opening. So right now the water can get from the Atlantic and the Pacific to the Arctic Ocean. We're not actually sure if that was true, if it was like if it was isolated or not. If you seal it off, it's much harder to simulate the Eocene. If there's a little opening, it's much easier. But in terms of the global picture of ocean heat transport, surprisingly, moving the continents around doesn't seem to change sort of what's happening in the tropics very much. It's a surprising fact. That's what these models, if you believe them, are saying. So, yeah, I think that's good. Okay, questions? Yeah, so we'll skip the snowball. Keep going, snowball.
The question is for you to do the snowball.
Okay, we'll do the snowball. Okay, I'm glad everyone's excited about the snowball. This is actually, so there's a crazy professor at Harvard who's sort of promoting the snowball. And he's really a wacky guy and really smart. And basically, he wrote an article in Scientific American about it when I was in high school. And that was sort of what got me interested in earth sciences. So I'm very happy later to be able to work on it again. But this picture is actually from the Scientific American article. And it's an artist's interpretation of what the snowball looked like. For what I'm going to talk about today, it's important that you don't consider this as the do-all, end-all of what the snowball looked like. So if there were a snowball, we do think that all the oceans were frozen over. But we don't necessarily think all the land was frozen over or covered with ice and snow. There may have been open regions of land. The analogy is at the last glacial maximum, even though it was really cold in Siberia, there was no ice sheet just because there wasn't enough precipitation. There were ice sheets in Europe and North America, but not in Siberia. Okay, so how do we know about snowballs? So I said before, this happened 600 million years ago. So most of our climate data doesn't go back that far. And it all comes down to looking at rocks. So it turns out there's a whole field of geologists, and for hundreds of years they've gone around and picked up rocks and chipped them and looked at them and argued. And now they can tell these amazing stories about stuff that happened 600 million years ago. on their study of rocks. It's very impressive. But these are some pictures of the sorts of evidence that indicate there was a snowball. So, first of all, this is the most basic piece of evidence. You find all over the planet at paleo latitudes of near the equator, you find these scratches. And geologists consider this very strong evidence of glaciation. So they only see these in the record when there were glaciers scraping over rocks and making these scratches. So that's sort of the first piece of evidence. The second piece of evidence that's important are these, what's called drop stones, these guys. And so you have these, what's interpreted as a shallow marine layer, these layers, and in the middle of them there are these weird rocks that don't belong. And some of them are as big as a person, you know. And the only way anyone understands these is getting into such shallow marine layers is a glacier flowing from the land, grabbing these rocks and dropping them off into the shallow marine layer. And so that's the interpretation of what's going on here. So that means not only were there glaciers at the equator, because we have glaciers at the equator today, but they're at 4 kilometers. But there were glaciers at the equator at sea level. So that's something that's very weird. Low altitude glaciers at the equator. Now there are a couple more nuanced pieces of evidence. For example, I'll talk about, these are actually what's called banded iron formations, and that's important for the snowball hypothesis. I'll talk about that. And the other thing is, not only do you find these, this is really remarkable and surprising, not only do you find these glacial features, but right on top of them you find rocks that only form in the very warmest conditions today. You find rocks that only form in the Caribbean or somewhere like that, carbonate rocks. And this is an example of a glacial, and so this over the millennia has gotten, rotated. But this is a glacial period, and then on top of that is these hot rocks, and this is sort of a better example of that. So you have a glacial type of rocks, and right on top of that you have these, large cap carbonate or cap dolomite, this type of rock that it forms in very warm climates. So those are the observations. And one more thing about the iron. The iron, it turns out, is a very important piece of evidence for the snowball, because here is the time before present, and this red curve is oxygen in the atmosphere, and it's a bit fanciful. We know that at some point oxygen was 0, and we know that now it's 21% of the atmosphere. But how we got from here to here, we don't exactly know. But we know that for the first, that more than 2 billion years ago, we find these iron formations, a lot. They're found all over the planet. And that indicates the oxygen was low. Because if there's a lot of oxygen, it oxidizes these iron formations, and you don't get pure iron levels. Then they stop, which indicates the oxygen must have gone up around then. The only time in the past 2 billion years, the only time you ever find these is during these pan-glacials, snowballs. What that's interpreted as indicating is that the ocean was entirely covered with ice, which sealed it off from oxygen and allowed the anoxic conditions that made these banded iron formations. So that's a very important piece of evidence for the snowball. But now the hypothesis, which there's sort of a diagram up here, that ties this all together, the snowball hypothesis that explains all of these things, you can see in a simple climate model here. And this climate model predicts the line to which ice extends. If it goes to 0, then ice at the equator, and you're in a snowball. If it goes to 90 degrees, that means there's no ice anywhere on the planet, and you're in sort of an equable climate. And if it's somewhere in between, you're in sort of a modern climate. And each of these dark solid lines is a stable state of this climate model as a function of the CO2 concentration. So it means that our current CO2 concentration of about 4 times 10 to the minus 4, if we were in a snowball, we'd be happy in the snowball. We're also happy here, and we could potentially also be happy in an ice-free condition. And this is a characteristic of a very nonlinear system, and it's nonlinear because of the ice albedo feedback. So when there's ice on the planet, it reflects away a lot of sunlight, and it's colder, and it's easier for ice to exist. And when there's no ice, the planet absorbs more sunlight, it's warmer. So basically, we sit here, and 600 million years ago, the sun was actually 6% less bright. So it was already easier to go in the snowball. And the idea is, we could talk about why later, we're sort of running out of time. Basically, for some reason, the CO2 decreased. And slowly you approach this point, which is, it's a bifurcation point, where this stable state disappeared. And then you jumped all the way down to ice at the equator. And so you started freezing over ocean water at low latitudes. And as you froze over the ocean water, there was, less light was absorbed and it got colder, and quickly you jumped into the snowball. Then, when you were in the snowball, you slowly increased the CO2. And the reason that happened is volcanoes kept putting out CO2, but the normal way CO2 is removed from the atmosphere is by a reaction of rainwater with rock on the surface that requires warm temperatures. It was so cold and so little precipitation, that reaction was shut down. The CO2 got really, really big, and then you jumped out of the snowball, and you got into an extremely warm period. And so this would be the cold rocks. If the ocean were ice covered, it would explain the banded iron formations. And then you would jump out like this, and this period would be when the very hot conditions, the very hot rocks were forming. And so this is a simple idea that sort of explains all these very strange pieces of evidence. And that's why it's appealing.
How long do they think it would take to jump from the snowball to the ice field?
Yeah, 10,000 years or less,
Wow.
we think. There's some debate about that. But this period is really long. And it's surprising because the glacial rocks are thin, but the cap carbonate is extremely thick.
Yeah.
But we think that the glacial period was millions of years, and this was tens of thousands of years. So the thickness of the rock doesn't necessarily correlate with the time. Okay, so there are various questions and issues with this, and that's something that I've worked on. But I think we should talk about that later, if anyone's still interested. Yep.
How do you get from the equitable climate down to the other stable climate?
Well, yeah, so here you would, for some reason, if the CO2 decreases for some reason, which a lot of people think has been happening over the past 50 million years with this gradual cooling, there are various ideas for why that might happen. Basically, either relating to the weathering, how the CO2 is removed from the atmosphere, or the volcanic CO2 input. These balance to control the CO2. And people have different ideas, but we don't know for sure. We don't even know what the CO2 was. But the idea is you decrease the CO2 and then you would go into a normal state. So I think I should skip, this is just stuff that I've worked on, but it's not that important. We got the real snowball. We talked about the real snowball picture. We can talk about that later. So the summary of what I've said today is basically what you should take away from this is that really strange things have happened in Earth's climate. It's not like everything was just constant until we started emitting CO2 150 years ago. There's been a lot of really strange stuff that we don't really understand that well, and that's why people are scared about climate change. Because we can't understand what happened in the past. And so we think that things that are happening now, they seem to be on the order of, the CO2 we're inputting seems to be on the order of things that caused huge changes in the past. And this is really an essential point. Some of these changes were really, really fast. So it's not like you had to sit around a million years to watch something change. It was like, 10 years, a very human time scale. We use a bunch of different methods to reconstruct the climate. And then we try to simulate it in climate models, improve our climate models and improve predictions. So if anyone has any questions, I'll take them, and if anyone has to go, that's fine.
Does the position of the land masses on the globe have a big effect?
Yeah, so it turns out that in most climate models, that can have a large effect. So I was just talking to the Max Planck people, and they take their CO2 from 280 parts per million pre-industrial to double that, 560 parts per million. That causes some amount of warming. But just moving the continents around to put them back in Eocene conditions causes the same amount of warming. So it can be a very large effect.
Yeah, two questions. If your snowball
One thing that I want to say is that Paul Hoffman, the snowball guy from Harvard, actually thinks that those are related events. He thinks that the snowball may have it may have helped to force the evolution of multicellular life, the extremeness of the snowball. But that's a separate issue. But in terms of whether, it sounds almost like you're asking if we could go back into a snowball. But since the sun is warming, it's getting harder and harder and harder to go back into a snowball. So it will be really hard to understand at this point.
Okay, my second question, your theory of the source of the carbon in the Eocene.
Yeah.
Being a die-off, either burning or...
Yeah, that was actually not the whole Eocene, but that very short period.
Would that appear as extinction event?
Would you see it? Yeah.
Well, wouldn't it show if it's extreme enough to alter the climate?
Yes, yeah.
To my knowledge, there's only been 5 major mass extinction events before.
Right, so so actually so the idea I was referring to was slightly, it was more that the idea was that there were these continental seaways that had accumulated a lot of biomass and that they sort of dried up and that they released a bunch of CO2, and that was the trigger. They burned and dried up or just oxidized. So something wouldn't necessarily go extinct. It would just be that a bunch of old dead stuff oxidized. On the other hand, then the idea is that would cause that would make it hot enough that you would start to see things dying, but they don't have to necessarily go extinct. It's just like 90% of them can die. Because you're right, we don't see a huge extinction there. What you do see more of is a spread, a change in what plants and animals live in different places, more than extinction. That answers your question. We can talk more later.
I understand that over hundreds of millions of years, the sun is considered to be warming.
Yes.
And I understand that over the course of a very short period of time, the sun's energy seems to be fairly constant. But over the period of time of, say, the last 50,000 years, do we have data as to how much variability there is in the sun's energy output?
I am not aware of such data. We do know that the amount that we have a reasonable theory for how so as Earth goes around in its orbit, its orientation wiggles and wobbles. We have a good theory for over the past 50,000 years, the orientation of the Earth, which controls where, at a particular place and in a particular season, how much energy you get. But in terms of the actual output of the sun over the past 50,000 years, I'm not aware of any measurements that show what it was.
Because we know there certainly are huge numbers of variable stars, and variability in star output is all across the map.
So my understanding was, maybe Eric knows better than me, but that if you study stars like our sun, they don't vary quite as much. They don't have huge, order 1 variations. But David,
Well, there are the cosmogenic radionuclides in ice cores. I don't know how far back they go, but they give some indication of the intensity of the sun.
or at least in certain wavelengths.
And so when the sun is more intense, it has a stronger magnetic field that shields the Earth better from cosmic rays. And then you find these products in ice cores.
But do you know if they indicate in the past 50,000 years how much the sun has changed?
I don't know how far back in time they go. They go back through the last several thousand years of these.
Do you have an indication about how stable the energy was output during those last several thousand years?
No, I know that it was cooler during the little ice age, so it was longer millions.
So my understanding is the people that want the sun to be driving climate, they don't rely on solar output, but they want the sun to change in certain frequency ranges, which affects the ionization of things high in the atmosphere, which affects clouds. That's sort of the mechanism they have. Because I think they even acknowledge that change in total solar output isn't enough to cause observed temperature changes. And then if you affect clouds, you can affect. That's my understanding of what they want, but I'm not sure about the evidence. Yep.
They're from geophysical sciences, I suppose.
Yes.
Why don't you guys take the winter series of Saturday lecture?
Well, I don't know. They probably have someone lined up.
We're going to take questions up the front.
Oh, yeah.
Name it after J.B. Smith or George Schlotzman or one of those guys.
That would be cool, yeah.
Fun.
Yep.
Okay, you seem to be ignoring Lovelock's equations, if you will, with respect to balance point for the biosphere versus the geological.
Yeah.
You also seem not to hit on the methane component very strongly, which could be enormous since it's a 25-to-1 ratio as far as global warming is concerned.
Well, yeah.
CO2 versus methane.
Yeah. So,
Okay, in addition, you've got Laurasia and some of the other continental drifts
yeah.
that occurred during this period, which were very important
Yeah.
for the isolation of things like the depth of sea,
Yeah.
right?
Yeah. So, yeah. So. Yeah. So you mean about the equable climate period?
Well,
So if we just focus on the equable climate period, the reason that I don't think methane could explain it is methane is very variable and has a very short time scale. This thing lasted for hundreds of billions of years, or tens of billions of years, order of 100 billion years. So if methane is the explanation, it's easy for methane to just be wiped out of the atmosphere compared to CO2 was regulated on a very long time scale. So it's harder for me to believe the methane explanation.
by what mechanism to remove them?
Well, things, if you take out the methane sources, methane immediately drops much more quickly than CO2 does. But in terms of the movement of the continents, we know that however they move, that can't be the explanation because throughout their movement, the climate persisted in this warm state.
Okay, with respect to the movement and methane,
Yeah.
methane is currently sequestered to some degree as the hydrate in and around continental shelves where it is buried
Yeah.
and will not come back out until the shelf moves and opens up that area to either ocean floor or something of that sort. So I'm not talking about methane generation in bogs and that sort of thing, which is a current cyclic phenomenon.
Right.
But there are loggers of various sorts for this that would hold it for long periods of time, requiring geological change in order to release.
Right.
And I don't think that has been discussed. I'm not saying that what you're showing is wrong. What I'm saying is there are additional factors that need to be brought in.
It's true, yeah. I mean, it would be hubris to claim that we include everything in the climate models. That's certainly false. But we can talk later.
Yeah, one thing that I don't understand is why the inclination of the Earth will change the input of the energy from the sun, because if you have that diameter of the Earth, and that's the circle that receives the energy, regardless what inclination.
Yeah, so we should talk about that. That's sort of, I think it's a good time to break, and I want to talk more with you about that.